So, a very good morning to all of you. Myself, Dr. Jennifer Sultana, HOD and Assistant Professor, Department of Electronics and Communication Engineering, Swami Vivekananda University, Bharat. So, today I'll be giving a short lecture on the interdisciplinarity of nanoscience and nanotechnology. So, basically, before going the subject of nanoscience and nanotechnology, we should first understand that why in different branches of science, let it be physical science or chemical science or biological sciences, nowadays there are implementation of nanotechnology. So what is the reason behind that? Is there any particular reason or is there any particular goal that is need to be achieved by implementing nanotechnology? So few of the questions that we need to answer right now nowadays that in terms of physics or in terms of electronic sciences if you consider. And as we all know that day by day there is a miniaturization of the devices. The chip size is actually getting decreased and hence we will be having a smaller sort of devices. So how is it possible to miniaturize such devices? This is the first question from the physics point of view. Next, if we consider from the biological point of view, then as we all know that, let's say consider for cancerous patients, then we have chemotherapy, right? So in chemotherapy, what is actually done? It actually damages whatever the cancerous cells are, but the disadvantages are it also damages your fresh tissues. So what is the after effect of that? There are many side effects and it will hamper the patient's health a lot after the chemotherapy. So is it possible for cancer patients to not to treat in such a way that not to have any side effects? Is it possible? So the question from the biological point of view, this is the question. Second, next, from the chemical point of view, if we consider that how do strain resistant materials work? So the answer to all these questions, all these queries can be answered in a simple way, that is the nanotechnology. The answer is nanotechnology. Yes, it is possible by the implementation of nanotechnology. Right? So that's why the subject I have chosen nowadays is its interdisciplinarity of nanoscience and nanotechnology. Right? So before going into the depth of the subject, let us first consider a few of the questions. Whenever you are listening the word nanoscience and nanotechnology, so what is the immediate question that is coming into your mind that what is the nanoparticle? How big is nano? What are the implementations of nanoscience and nanotechnology? What actually nanotechnology deals with? Right. What are the opportunities that are being hidden in this nano dimensions? Right. So these are the few of the questions that we need to first understand before going into the depth of the nanotechnology. Right. Now, simple question is, what is a nanoparticle? So nanoparticle here, as you can see here in the image, this is the fullerene ball. Now what is a fullerene ball? It is basically 60 carbon atoms that are linked together to form this type of ball sort of thing, and having a dimension, you see its dimension is around 1 nanometer. So the dimension is 1 nanometer, and such type of ball we can say it is a nanoparticle because its dimension falls in the nano region. Right? So the 60 carbon atoms linked together, it forms a nanoparticle. Now, next question will arise in your mind that how big is nano? How big is nano? How you can visualize the dimension that is nano? In simple terms, you can say that 1 nanometer is 10 to the power minus 9 meter. Fine. But if you want to visualize the fact, if you want to visualize the parameter, so what most common example is you consider the diameter or the dimension of the earth, right? And then on top of that, you consider the diameter of a football. So if you take the ratio of the diameter of the earth to that of the diameter of the football, whatever factor or whatever value you are getting, similarly, the same thing if you take the ratio of a football diameter of a football and the diameter of a fullerene ball, you will get the same diameter, same dimension. So now you visualize, you just close your eyes and visualize that, okay, diameter of the earth and then diameter of a football. So how is the difference? What is the difference? How huge is the difference? So the difference is in that nano dimension. What is the difference? The difference is nowadays if you look into bulk In the bulk properties, whatever is visible by our own eyes, but whenever we are going into nano dimension, that is not visible by our own eyes. So some of the properties or some of the material characteristics that is actually getting changed whenever we are going into nano dimension, right? So in the scale, in the ruler, if you want to visualize that, if you know this is a millimeter or the centimeter scale, so it is a millionth of a millimeter or a billionth of a meter. Okay. So now, is this changes in the nano dimension? Is it visible to us, or can you feel that changes? So the common example is your own finger, human fingernail, that actually grows 1 nanometer per second. Can you feel it? No, you can't have a feel of that. For another example is a man's beard that actually grows 5 nanometers per second. Can you feel it? No. So this is nanodimension, that you can't have a feel of that, you can't see that, you can't feel that, but you have some of the changes or some of the properties are getting changed in a good dimension, in a good way, so that we are implementing nanotechnology in different branches of sciences. So another example is, you see here this image. In this image, this thing is a strand of a human hair, one single strand of your human hair, and on top of that there is a silver nanoware kept on top of that. So you see the difference. You see these figures are just to make you visualize the parameter, the fact that how small is that. Okay. So what is nanoscience? So nanoscience is basically the study and manipulation of materials at nanoscale. Whenever we are taking any material at bulk scale or at a bulk dimension, then we are looking at its properties in a bulk. But whenever we are considering its change in property at atomic or molecular scale, what is happening at such atomic level or in molecular level, that particular thing we need to capture or we need to understand, that will be understood by using nanotechnology or nanoscience. Right? So now the question is, 5 nano, we can't see that, we can't have a feel that it is happening, so we need to take some help of some special instruments to see this nano dimensions. Then why we are going to nano dimensions? It is fine, we are okay with the bulk dimension, and why we are going into nano dimension? The reason is, there might be some of the advantages that for going into nano dimension. So what are the advantages? The advantages are, at nanoscale, strange things happen to the materials. That is, their properties can change. So for a particular material, the main property, whether it will react or whether it will have any applications in any of the dimensions, that is actually determined by its reactivity. So this reactivity, whenever the particle size is getting varied, the reactivity is also getting varied. There is change in reactivity. Fine. Second is the size. The smaller the particles, they have different sort of optical properties, right? So you know that whenever if you are seeing an object red, means what? It is actually capturing white light and it is reflecting back red wavelength of light. So that particular wavelength is captured by our human eyes, and we are seeing that particular material as a red material, red color, right? So whenever you change the diameter or you change the size of the particles, then its optical properties, means which color it will absorb, which color it will reflect, that is getting altered, and hence the color of the material will get altered. Fine. And then magnetism. Smaller particles may have different sort of magnetic properties and so on. So these are the few of the properties that are actually getting altered and which will have a huge impact on the particles on that particular material's applications. Fine. So now let us first see this example, that reactivity, how reactivity actually matters or how actually it alters the particular material's properties. So first, here you see it is, we consider a cube, and let's see the dimension, like this side, the scale length. This is, let's say, 2a, twice of a. A is a particular dimension, so this is 2a. Fine. So this is a cube having a diameter, having a side length of 2a. So what will be the volume of the cube? We all know that the volume of a cube will be side whole cube. So 2a whole cube, we have 8a cube, right? Next, if you consider the surface area, what is the surface area of this particular cube having a side length of 2a? That is 6 into side length square. So that will be your 24a square, right? So the volume of this particular cube is 8a cube and its surface area is 24a cube. Now this particular cube, if you want to react with some other material, then which particles or which atoms will be more prone to reactivity? Only the side or the boundary particles. The particles that are inside this particular cube, that will not react as much to the extent that those particles that are present at the boundary of the cube, those will react, right? So to measure the reactivity of a particular material, we need to calculate the surface to volume ratio. Surface area to volume ratio means whatever volume is present in that particular cube, how much part of that volume is actually getting activated or is actually reacting whenever we keep this particular particle in some chemical reaction. So for this big cube, if you want to calculate the surface area to volume ratio, then the surface area to volume ratio will be your 24a square by 8a cube, and that will be your, what will be the result will be 3 by 8. Fine. Now if we break this particular cube into 8 different cubes having same dimension, the dimension is, if it is 2a, then this will be a, only a. So this particular cube or this particular cube having dimension a, so what will be the volume? Volume will be 8a cube. And what will be the surface area? The surface area will be 6a square. So now for this smaller cube, if we want to calculate the surface area to volume ratio, then what will be that ratio? That will be coming as 6 by 8. So for this big cube, we have the surface area to volume ratio as 3 by 8, and for this small cube, we have the surface area to volume ratio as 6 by 8. So whenever we are reducing the size from this bigger particle to smaller particle, what impact is it is getting on its reactivity? Its reactivity is getting doubled, right? For this it is 3 by 8 and for this one it is 6 by 8. So it is getting doubled. So means you can think of in such a way that whenever we are reducing the particle size, then our reactivity is getting increased. Means whenever we are shifting from a bulk material, same composition, same atomic composition, everything is same, only the size is a bulk material, and that particular same material to we are shifting it to a nanomaterial, nano size, then definitely its reactivity will get increased, right? So this is a common example to make you understand that what actually changes, how actually the properties are getting changed, right? So another example is, you all know this granulated sugar, and these are sugar cubes, same thing, same sugar, but which will dissolve faster? Definitely granulated sugar. So granulated, this is also a sort of reactivity, right? So granulated sugar will dissolve faster. Why? Because of the particle size. Okay. So these are a few of the examples that I'm trying to make you understand that what actually is changing whenever we are going to nano dimension or whenever we are dealing with nanoscience and nanotechnology. Right. Now, it is basically a question of science. Micro, macro, nano. Macro means it is a bulk size, right? Micro means of the order of micrometer, and nano means of the order of nanometer. So if you consider these type of materials, 360 carbon nanotubes, silver nanoparticles, these have dimensions of the range of 1 to 100 nanometer, means these are nanoparticles. If you consider a virus, or if you consider some bacteria that typically have a size of few microns, and next, if you consider human cells or some cells or some human hair, these typically having a few microns, a few millimeter, a few centimeter of dimensions. So this is a difference, macro, micro and nano. Fine. So now, actually visible light, if you consider that how the optical properties is actually getting changed. So visible light is basically white light. In white light, what is the visible spectrum? It ranges from 380 to 740 nanometer. This is the spectrum, or this is the part of the white light that is actually visible by our human eyes. Fine. So now this is purely all know. Now the thing is, spectrum. If you see the different wavelengths of the spectral colors, so red, orange, yellow, these particular wavelengths in nanometers, right? So a particular material or a particular size of material that will reflect red color is showing its color is red means it is reflecting a wavelength varying from 780 nanometer to 625 nanometer. Then only we will be able to see it as red. If something we are seeing it as blue, means it is reflecting the light of 500 nanometer to 435 nanometer and so on. Right. So now what actually happens is these optical properties are totally dependent on the size. So how? So example is like silver and gold nanoparticles. If you see from this picture. So these all are actually gold or silver nanoparticles. But what is the difference? The difference in color is because of the difference in their particle size and nothing else. The chemical composition, gold or silver, whatever you take, this is the same chemical composition. Nothing is getting changed. Only the particle size is getting changed. So by changing only the particle size, we will be able to change its optical properties or color. And you all know that in physics or in electronics, there are many applications that are actually based, whose basic is actually the optical properties of a material. For example, in solar cells, in photovoltaics, or in LEDs, whatever LEDs you are seeing. So, depending on the particle size, if it changes the colors, means depending on the particle size, it will change its efficiency also. Right? Means it will change its optical properties and finally its efficiency also if you are considering some optoelectronic devices. Okay. So now this is a very good example. Like see gold. You all know bulk gold, whatever ornaments or whatever things you actually wear. This is actually this golden color, bulk gold, fine. But this particular red color liquid and these different purple and red, different colors of liquid and nothing, all are gold. But what is changing? Only the particle size is getting increased. So as the particle size is getting changed, you have a change in color of that particular material. Right? So the conclusion is different sizes of particles reflect and absorb light differently, and hence we can alter the optical and ultimately the optoelectronic properties by altering only the dimension of that particular material. Clear? So now the thing is it a new technology? Is it something that has been discovered few years back only and we just came to know right now? No. It was previously also known. See, these type of paintings you have seen in different monuments long years back, right? So that time, whatever color it is actually showing, it is gold nanoparticles having different dimensions. So at that time, it was called what we know. It is a painting or it is an art. It was known as an art. But now we know that it is nanotechnology, and hence nanotechnology has different applications in different dimensions of sciences, may it be physical, chemical, or biological, whatever you consider, right? So now the question is, so what is nanotechnology? Is that the development of materials and devices by exploiting the characteristics of particles on the nano scale. Means if in the nano range we can alter that particular characteristics by us, if we can alter, then what will you get? You will get different sort of same thing but different sort of applications or different sort of properties. So that is actually nanotechnology, right? So there are various potential impacts of nanotechnology in different domains of sciences, as I already mentioned in healthcare, diagnostic, cancer treatment. There are nowadays what is coming actually targeted drug delivery means whatever in cancer patients they are with the help of nanotechnology they are doing targeted drug delivery means that particular drug it will only target particularly cancerous cell and it will remove that or burn out that. It will not hamper the side by good cells. So what will be the result or what will be the implication on the patient's health? That the patient will not suffer from any of the side effects that earlier therapies like chemotherapies that is having. There will be no side effect. right? Next, there are actually nanotechnology implementation in different cosmetics, sports industry, and of course, electronics is one of the major area or major industry you can say where there is very much implementation of nanotechnology nowadays. You know that there is faster, more slim and sleek design of computers and laptops you are getting, and much more facilities are you are getting. So how it is possible? It is because we are miniaturizing the chip design or the chip size with the help of what? With the help of nanotechnology. And at the same time, with miniaturization of the device size, we are getting a faster device, right? Because we are handling with a smaller sort of device size, right? So there are various potential impact in nanotechnology, different cleaning, different chips are being prepared. This paper type of solar cells are being prepared. So I'll not go into the details of this. But only thing is that it has interdisciplinary applications in different branches of science. Now the question is that how will we be able to prepare such small things? As we can see, you have seen that nanotechnology is something that we can't be able to see with your human eyes. So the question is how will we build that? So there are two ways out, right? The first thing is top-down approach. What is a top-down approach? You consider a bulk material, a bigger material. You start on cutting, and you end up with a dimension of having nano range, right? So this is the top-down approach. Second is the bottom-up approach. So what is the bottom-up approach? You start with some of the molecules or some of the atoms, and then you start piling one above another, one above another, like that, and you stop whenever you are getting that particular nano range, right? So these are the two different approaches that by which the nanoparticles are being prepared. Now the question is, we will be not able to understand, we will be not able to visualize these particles by our normal ear, by optical microscope, right? So there should be, beyond the magnifying glass, there should be some of the important devices or some of the important instruments that actually need to be implemented for visualizing or for characterizing such nano dimensions. So these are various of the instruments you can see over there. FESCM, TEM, these are various instruments. What is the actual procedure for working principle of that or the main material? The main thing is it acts on the principle of electron transfer, the electrons application. Like for example, in your optical microscope, what is the main thing? Your light is the main thing. By using light, you are visualizing the things. But in those microscopes, particularly for visualizing the nano dimensions or nanoparticles, what you actually need is you actually need electrons to propagate, electrons to get absorbed or to reflect back from such materials, and they will end up with some of the information or whatever you want to see. You want to see the chemical composition, or you want to see the surface morphology, or anything else. Whatever information you want, that will be brought to you by the help of electrons, not by the help of light. Okay. So in brief, whatever we have studied, in brief, what is nanotechnology? So 21st century has been projected to be the century of nanoscience and nanotechnology. Nanotechnology includes it actually deals the structure with dimensions having lesser than 100 nanometer in at least one direction. If you consider dimension above 100 nanometer, then it will go to macro range. That will be not a nanomaterial. But you need to consider materials having at least lesser than 100 nanometer in at least one dimension, right? And nanoscience it actually includes the study of materials at atomic and molecular scale. So such low dimension demands for such novel technologies for the fabrication of future nano devices. Right. So here from in this image, you see this image. This particular image is actually, this is a strand of a human hair. One particular strand of a human hair, and within this size is around 20,000 nanometers. So now, if we consider such devices, such nano devices having this interconnect lines or cross-sectional lines that is having the cross-sectional pads that will be having dimension of the order of few nanometers, then you can just imagine that within the cross-section of a human hair, you will be able to embed thousands of interconnect lines. within the cross section of a human hair. Right? So this is the advantage of nanotechnology. This is what we call the nanotechnology is. Right? So now, if we are dealing with such type of materials that are actually having dimensions in the nano dimension, we can't see by our human eyes. We can't have a visualization. We can't have a feel of that what is happening at nanoscale. Then, for the fabrication of such devices, of the characterization of such devices, we need to take help of some special technology so that there will be low defects in such materials. In a bulk, if you want to design a particular material in a bulk dimension, then what you can, by your own eyes, you can visualize, okay, this is the problem, this is the defect going on, so we need to rectify it. But in a nano dimension, what is going on, you won't be able to know at the time of fabrication. After fabricating the device, when you will be going to test it, then you will come to know, okay, there might be some problem during the fabrication process, and that's why I'm not getting particular efficiency or whatever particular application you are using that. So for that purpose, we need to use some particular technology that is called the clean room technology. So what is clean room? Clean room is basically a sort of room, a particular type of room in which the concentration of the airborne particles is controlled and which can be minimized by using some sort of arrangement, some sort of filters, so that we can adjust the temperature, the humidity, the pressure, and the total air ambient. That particular ambient you can control by your own, it is in your control, right? And such particular room is called a clean room, and this type of technology is particularly used for the fabrication of nano devices. Now, what is the importance? Why do actually we need clean room? Why we can't prepare the nano devices in normal ambient? The reason is, you see in this figure. Let's say these black two these things. These are the two metal contacts, the metal pads that you want to design in a particular device. And these metal pads are having a dimension of the order of few nanometers, right? So by using proper masking and everything and using sophisticated machines, you prepare this mask. But if you are preparing this particular material, this particular contact in your normal ambient, so what will happen? You can't see it. So what will happen? Let's say this red thing, whatever you are seeing, this particular is a particle, which is a dust, which may be a dust particle, or maybe some strains of your human hair, or it may be some fabric strains or something, anything else, which is having a dimension more than a nanometer, means in the micro dimension. And if it falls in between like this, so what do you actually get? You actually wanted these two metal pads separated with each other, but what you are getting a short in between this. So whenever you will prepare such type of mask, and this particular mask will be used for the fabrication of a particular device, and when you get to test such particular devices, what you will get, you find that whatever the efficiency you are expecting, you are not getting that particular efficiency. Reason is some of the metal pads in between the during the fabrication process only, they have damaged. Either they have been short circuited or they have been open circuited, depending on the type of the defects, whatever particle is getting on top of that. So your efficiency is getting decreased. So now, before that, I have already mentioned that nowadays in VLSI technology, you might have heard the VLSI, that is very large scale integration. In VLSI technology, what is actually happening? Various thousands of interconnect lines, or thousands of MOSFETs, or thousands of BJTs or FETs that are being implemented in a particular single chip. So in a particular single chip having an order of few centimeters, in that if you can embed thousands of MOSFETs, means in each MOSFET you have three particular contact areas. One is source, one is drain, and there is gate. You know this, right? So these three contacts into 1,000 particular devices means 3,000 contacts in a chip dimension. What is the chip dimension? Few centimeter. Let's say 1 centimeter. So in 1 centimeter, 3,000 contact lines means you can just imagine the size of the contact pads. They are in the nano dimension. So after fabricating the device, after everything, after whenever you are simulating such particular device, you are getting a very good efficiency, fine. But whenever practically you want to test that device, at that time, what you are getting? You are getting a low efficiency, because few of the interconnect lines in between they have already getting damaged. So out of 1,000 you will see only 500 or 600 MOSFETs are working and others having damaged, others having got damaged because of such interconnects or such problems, right? So this is the thing, this is the importance. So airborne concentration is basically the number of particles or the number of bacteria generated per minute divided by the total volume of the air supply. So this is definition of the airborne concentration. So by using clean room technology, what you can do, you can actually control the airborne concentration. You can control each and every parameter of your ambient so that you have a good control of whatever you are fabricating. Okay, so this is the thing what you wanted and this is the thing what you get. This is the difference. So these are the basic terms of clean room: air lock, air shower, HEPA filter, sticky mat, alpha filter, HVAC, and finally is the AHU. This is the thing, air handling unit. And this air handling unit comprises of all these things, whatever I have mentioned here: air lock, air shower, HEPA filter, alpha filter, all these things. And these particular components, I'll not get into detail of that, but these particular components, they will be having a control. Each and every particular component will be controlling the ambient of that particular room. So clean room usage is contamination type and control of IC design that will understand that yield improvement is the biggest challenge in integrated. Nowadays, IC technology, whatever by implementing nanotechnology, whatever IC you are getting designed, so the main thing is you need to improve the yield. That is the biggest challenge. Right. So during the fabrication process, you need to sort out those things during the fabrication process. Okay. So by using clean room technology, you can eliminate all those problems that are being happening during the fabrication process. So here you see these are the two metal lines and these are the dust particles. So if it falls like that, it will short circuit. If it falls like that, it will make it open circuit. I have the same images also. See, these are the conducting lines and this is some sort of dust particle or some particle present in the air and it is falling like this. So what it will create? It will actually create an open circuit in between these interconnect lines. Next, if we have a interconnect lines like this and if we have a short circuit like this, let's say this particular material, this particular material, let's say this is a conducting material. So what it will cause, it will conduct, means it will making a short circuit between these four lines. Okay, so this is the difference of how these particles are getting, from where do we get this particle? From the people working in the fabrication lab, generated by the fabrication equipments or the processing chemicals. Right. So these are different contamination types. The first one is particles. Second one is metal ions. There may be different type of metal ions that you will get from previous fabrication process or the previous steps, and those will also hamper your clean room, the fabrication device fabrication. Next, the chemicals, the airborne contaminants, all these particular to sort out or to make all these particles, to remove all these particles, to remove the impact of all these particles from your fabrication technology, what you need to do, you need to prepare those particular nanomaterials in a particular room that is called a clean room. And this clean room, by using this clean room technology, you will be able to make devices better or you will be able to get more efficient devices. The common example is like if you can say a same thing, an electronic gadget of different companies having same specifications, but they are having a price difference. So why that price difference is? Because of this thing, because of the fabrication technology. Because of this fabrication technology, let's say one company has prepared that particular device in a clean room by using clean room technology, and another company has prepared that same device but in normal ambient. So the difference will be in the efficiency, the difference will be in the lifetime. Right? So these are the big problems and these are the things. So the main conclusion that I want to draw from here is nanotechnology nowadays an emerging domain in every branches of sciences. In case of you will get in jobs, in technology, entertainment, in health sector, each and everything, in each and every branch of science, there is a huge implementation nowadays and coming also in near future also. Next 50 to 60 years, nanotechnology will be the dominating area either we consider in R&D, research and development, or in considering jobs, or in considering health sector and different sectors. So this is the future actually. Okay. So a very much thank you all of you for hearing this session. Thank you.